While in hypoxic condition, is it logical that our body elevates the insulin level and the glucagon level? Hypoxia results in deficit in energy generation in a cell unless necessary measures are taken to make a compensation. This is where biopathway called glycolysis comes into play, in which a molecule of glucose is divided into two molecules of lactate acid, contribute 2 units of bioenergy, or 2 ATPs, totally without oxygen. Just remember, ATP is a unit of bioenergy, just like a kilogram is a unit for marking the weight. And you don't have to know more about it. Opposed to glycolysis in glucose oxidation, which is glucose metabolism under sufficient oxygen supply, a molecule of glucose contributes 38 ATPs. Make a simple math. 10% of shortage in energy due to hypoxia should be compensated via glycolytic pathway with 180% increase in glucose molecules. Say a cell needs 380 ATPs in a given time. Under sufficient oxygen supply, 10 molecules of glucose oxidation can do the work perfectly. C, 10 molecules of glucose oxidized, each of which contributes 38 ATPs, and we come up with 380 ATPs. However, with a 10% deficit in oxygen supply, 9 glucose molecules get enough oxygen, generating 342 ATPs of energy, and the remaining 38 ATPs of energy in shortage can be compensated by 19 molecules of glucose via glycolytic pathway, because a molecule of glucose generates only 2 ATPs of energy by glycolysis. Our body is designed to do its best to meet the energy demand of all its cells, because any cells with less than enough energy generation is to be with many physiological problems. Therefore, while the blood is not able to deliver oxygen as much as needed by cells around the body, increasing the delivery of glucose is a rational option to compensate energy shortage by glycolytic pathway in any cell. As we concluded above, compensation of energy shortage by glycolytic pathway consumes large amount of glucose. How to deliver large amount of glucose to the cells around the body? Firstly, insulin secretion should be increased, because with a higher insulin level, cells can absorb more glucose more rapidly from blood. While glucose in blood is taken up rapidly by cells around the body, the glucose content in circulation decrements as quickly, which should be replenished as quickly. Otherwise, a low level of glucose in blood or hypoglycemia turns up shortly. To maintain reasonable level of glucose in blood, there should be supply of sugar to the blood at the same speed as quick as taken up under hyperinsulinemia. Therefore, secondly, glucagon secretion should be increased as well, because under hyperglucagonemia, liver releases glucose rapidly, replenishing the blood as quickly. In other words, insulin and glucagon work in collaboration. The former is responsible for delivery of glucose from blood to cells, and the latter responsible for release of glucose from the liver to cells as quickly as taken up by cells with the aid of insulin. Now we have speculated to come up with a theory that under hypoxic condition, our body should be designed to stimulate both insulin and glucagon secretion, boosting glucose delivery to cells and compensating the shortage of energy resulted from deficiency of oxygen. There are plenty of medical scientific papers looking into insulin level and glucagon level of obese people and type 2 diabetics, echoing our theory. I wrote a paper trying to elucidate at a subcellular level on how both insulin and glucagon are regulated. The paper is available online, titled How Lactic Acid Regulates Secretion of Insulin/Glucagon and How Hypoxia Causes Elevated Blood Pressure, Obesity, and Diabetes Mellitus. Note, as for glucagon in this paper, at the initial phase, with the increase of lactic acid production or with elevated glucose level under sufficient oxygen supply, glucagon secretion decreases. And while membrane hyperpolarization takes place, which is possible only under hypoxic condition, the more production of lactic acid only stimulates the more secretion of glucagon by islet A cells. This paper perfectly tells why secretion of insulin and glucagon behaves the way they do. To sum up, there are 2 points to make. First, hypoxia causes obesity by elevating insulin level and glucagon level. Second, hypoxia causes death of islet B cells, resulting in type 2 diabetes mellitus. Since at the beginning of a prolonged hypoxia, the number of living B cells is sufficient, secreting enough amount of insulin to maintain glucose level at normal for quite a long time. That's why obesity always precedes the type 2 diabetes. Note, obesity is not the causing factor for type 2 diabetes. Next, let's do a case study to see if insulin and glucagon secretion is affected by hypoxia. Hyperglycemia causing RBC's rise is a good example about my theory on regulation of insulin. After meal, everyone feels sleepy, more or less, because meal ingestion is followed by elevated glucose level in blood, which in turn causes RBC's rise, causing whole body hypoxic, which is why we are sleepy more or less after a meal. Take a look at this table again. Normal control represents healthy people. T2DM is short for type 2 diabetes mellitus. I would finger 6 points. First, during fasting, T2DM group has higher insulin level than normal group because T2DM is hypoxic, where, according to my theory, insulin secretion is stimulated. That is significant when you consider the fact that the number of living islet B cells in T2DM is far less than healthy people. Second, after meal, insulin levels of both groups climbs because both groups become more hypoxic than during fasting. Third, there are 2 factors causing insulin levels of normal control people climbing steep curve. See from 7.3 to 53.7 to 68.2. 1. RBCs become markedly rigid under sudden emergence of hyperglycemia after meal, causing whole body hypoxic, which stimulates insulin secretion markedly. 2. The number of living B cells of a normal control group is sufficient. Fourth, There are two factors causing insulin level of a T2DM group riding milder curve. One, the meal caused body hypoxic further, but not as much as in normal control group. Because RBC of a T2DM group was already rigid before the meal. Two, the number of living B cell is far less in T2DM people. Fifth, 120 minutes after meal, insulin level of a control group gets back to normal because then glucose level returns to normal and the flexibility of RBCs recovers automatically, and the body is no longer hypoxic. Sixth, the insulin level of a T2DM group is far less than enough to clear blood sugar within 120 minutes after meal. Therefore, glucose level is still higher than duration of fasting. Accordingly, flexibility of RBCs is still worse than fasting, implicating that body is more hypoxic than fasting duration, which causes more insulin secretion. Above 6 points are good evidence testifying for my theory on regulation of insulin. Additionally, in this table, glucagon levels of a type 2 diabetes group are always higher than normal control group, fasting or after meal. That's because type 2 diabetics are more hypoxic than healthy people, and unlike islet B cells, which secrete insulin and die under hypoxic condition, islet A cells, which secrete glucagon, however, endure well under hypoxic condition. Therefore, the number of living A cells of type 2 diabetics is no less than that of healthy people. While cells acquire sufficient oxygen, glucagon level decreases accordingly, and the liver no longer releases at a high rate as glucose stored into circulation. With glucose entering the circulation at a normal rate, normal insulin level can process glucose handily. Therefore, we get two conclusions. First, adipocytes no longer absorb nutrients at a high rate, and the fat store ceases growth. Second, as long as the number of living B cells is not too few, secreting enough insulin to handle glucose entering the circulation at the normal rate, type 2 diabetics mellitus can be cured. Note, clearing of glucose after meal takes far more lot of insulin than basal, which may cause a stress to X-type 2 diabetics even though they are hypoxic free if the number of living B cells is in alarming range. As additional information for obesity, to promote release of fat from adipocytes, adrenaline or epinephrine is the key factor. Exercise or spicy food promotes secretion of adrenaline.